Hello, everybody. I'm Mohammed El Ashri, a PhD student at Imperial College, and I'm going to talk about the 3D modeling for masonry arch bridges. So masonry arch bridges represent about 50% of the current UK's in service stock for railway and roadway bridges. However, due to the long service life of these bridges, they have deteriorated under the effect of increasing traffic loads and extreme environmental conditions. And to replace this larger stock of bridges, this would impose high economic and environmental costs. And this creates an urgent need for having reliable assessment for the current masonry of arch bridges. However, most of the current assessment methods are currently 2D, and they mostly ignore the transverse behavior for these bridges under eccentric loading effects, and as well as the contribution of spandrel walls. So to address that, 3D modeling approach is considered, including the main components of masonry arch bridges, including the arch, the spandrel walls, and backfill, where a 3D mesoscale representation is considered for the masonry parts, whereas a continuous elastoplastic modeling is considered for backfill. And to consider the interaction between the different bridge components, nonlinear interface elements are used as physical interfaces. All of this is implemented within a nonlinear program called Adaptic, which is an in-house finite element program, along with a parametric modeling tool to generate different bond patterns and to improve the computational efficiency of these large models. A domain partitioning approach is considered. So the presentation is going to go through validation and understanding some behavioral characteristics for masonry arch bridges, and then some simplified modeling. So starting with validation, the tests performed at Bolton Institute are considered. And in this presentation, I'm focusing on specimens 3.1 and 3.3, which are almost identical, except for the fact that the spandrel walls are detached from the arch barrel in the 3.1 specimen. So when validating this, we found a good agreement between the numerical and experimental for displacement response, as well as the failure mode, where the numerical model managed to capture the four-hinge mechanism for the arch barrel in the bridge 3.1. Moving to bridge 3.3, again, the low displacement response showed a good agreement between both the numerical and experimental responses, as well as failure mode for the arch barrel. In addition, here we have the spandrel walls. The crack pattern for the experimental crack pattern was in good agreement with our numerical model capturing the main features of the failure mode. And to ensure consistency within our numerical models and for the calibration of our material models, we used some material properties achieved from the material tests performed within the experimental program. And for the properties that are difficult to be computed experimentally, we depended on some sources from literature to assume these values with reasonable values. Moving to the second step, which is understanding some characteristics for the behavior of masonry bridges. So in this, we used a parametric study considering both detached and attached spandrel walls models. And in the detached models, the main difference is that the spandrel walls are excluded from the model, but we are providing restraint in the longitudinal direction to ensure that confining effect is provided. And it is we considered four different load positions as highlighted here. And the first feature that we investigated is the effect of the presence of the spandrel walls. And spandrel walls have mainly two functions in the behavior for these bridges. The first function is restraining upward deformations for the arch barrel. And this function is maintained as long as no fold detachment is happening between the arch barrel and the spandrel walls. And the second function is providing confinement for backfill against the transverse deformations. And this is also maintained as long as no significant out-of-plane deformation are happening to these spandrel walls. So starting with loading concentrically at midspan, and comparing the detached and attached response, we can see from the load displacement diagram that the attached response is showing some enhancement, which starts to deteriorate and converging to the detached response. And this is in good agreement with what we can see from the deformed shape in the attached case, where a full detachment is occurring at failure between the spandrel wall and the arch parallel. Moving to the second function, by looking at the top view, we can see that out-of-plane deformations for the spandrel walls are not significant. Therefore, the confining effect is maintained all over this analysis. Shifting the load at quarter span, we notice a similar trend in the response. And however, the response didn't manage to, it is converging, but it didn't manage to reach the detached case yet, because we can see that the separation between the arch parallel and the spandrel walls is not fully achieved along the whole thickness. And again, the confining effect is maintained here. Shifting the load eccentrically at closer to the spandrel walls, we can see that the enhanced response starts to deteriorate, converging to the detached one, and then it degrades more and starts to go below the detached response. This indicates that there is a failure in the spandrel walls, and this is in agreement with large out-of-plane deformations observed here. This becomes worse when shifting the load to quarter span, and we can see that the response becomes lower than the detached response earlier, indicating failure within the spandrel walls. Building on that, we investigated also the effect of the thickness of the spandrel walls on this case. So we added another case where the spandrel wall thickness is decreased to 220 compared to the previous 330 millimeter. And we can see that from the deformed shapes that there is a weaker wall is suffering from more significant out-of-plane deformations. And also this affects the failure load shown in green here. This indicates the importance of the inclusion for the spandrel walls in our models. The next aspect that is investigated in this study is the effect of the width for the arch parallel. And in this, we investigated three widths, 3 meter, 6 meter, and 9 meter. And we noticed that the load displacement response starts to converge here between the 6 meter and 9 meter to match perfectly. This indicates that for certain widths from the arch parallel, the cracks stop to propagate, affecting only a certain or a specific width of the arch parallel, which is almost the same in the 6 meter and 9 meter case. And this indicates that the effective width is already satisfied in the 6 meter case. So it's the effective width is somewhere in between the 3 meter and 6 meter. And moving the load to quarter span, we can see that the matching between the 6 meter and the 9 meter cases is less apparent here. And this can be indicated with the cracking here, where the full width cracks are seen in a 3 meter and 6 meter case, but not seen here, indicating that effective width is somewhere between the 6 meter and 9 meter. Building on that to develop our first simplification. So the simplification depends on relating 3D models to the 2D models with effective widths. And to calculate the effective widths, we are using the failure load from the 3D and the failure load from the 2D case. And to further investigate this, we considered increasing the width 1 meter in a time. And we noticed that starting from 7 meters, the ultimate load starts to converge as seen here, indicating the presence of a specific effective width. And this is further indicated with load displacement contours showing negligible displacement at the faces of the arch parallel. The final thing we are considering is macroscale modeling and comparing it to stretcher and header mesoscale models, and applying the load at concentrically at quarter span. So from that, we see good agreement in the failure mode and the load displacement response between the stretcher and the macro model, but the header model overestimates the response. And the reason behind that is difference in the failure mode, as we can see the ring sliding or ring separation in the structure bonds. To conclude, van der Waals play an paramount role in the overall behavior of masonry arch bridges, and this is summarized by restraining upward deformations as well as providing lateral confinement. Such effects cannot be captured unless there is an interaction between the arch backfill and the van der Waals, which cannot only achieved except for the 3D models. Batch loads resulting from single wheel effect affect a certain portion of the bridge width, allowing for the consideration of effective widths. And finally, macro scale models can provide reasonable prediction with proper calibration. However, it cannot differentiate between different bond patterns for the arch pattern. Thank you very much for your attention.